Okay. Ladies and gentlemen, this is the sheet that you have in front of you. And what it is it's a version of the periodic table, similar to the one we have up here in the classroom. And on this periodic table are numbers. These numbers are the number of electrons that are on the outside of that particular atom. What we're going to do today is we're going to focus on just some of the yellow highlighted areas and the gray highlighted areas. We are going to name them. We're going to fill in some information to help us. By the end of today, you should have an understanding of basically which elements will bond together. The focus of today is going to be ionic bonding. Okay, so let's start by going ahead and taking a few notes on the back of your sheet. Okay? Okay, so we're going to call this ionic bonding. It's up to you. I would recommend taking them portrait. Okay, so instead of landscape, which is kind of like the long sideways, do it portrait, kind of like what you see on the screen. All right. Please understand that everything we're going to talk about today are observations scientists have made over many years and information we've accumulated and we've tried to come to reason and understand. So all of the theories and ideas and everything we know about bonding has come from extensive study, experimentation, and conclusions by a large portion of the scientific community. What you're learning is considered to be fact. However, we're always adjusting in the model of the atom. We're always coming up with new ways to combine things. So this is a very simple version of ionic bonding. Atoms have more than, or all atoms have by nature a certain amount of electrons. Okay? If you look at a periodic table, they have the same number of electrons as they have protons. So for instance, and please write this down, if you're starting with, let's say, sodium. Okay, sodium has, by its very nature, change color here, 11 protons. That's what makes it sodium. Okay, that's what defines sodium. However, the way that sodium reacts with its environment, for instance, sodium is incredibly explosive when it comes in contact with water. Okay, the way that sodium reacts with its environment has only to do with those electrons that are on the outside of every sodium atom. So sodium has 11 protons, and typically speaking, it has 11 electrons. However, it has very, very special electrons within those 11. Sodium only has one, what we call valence or outermost electron. Valence electron. We call these the outermost electrons. And it's this one electron that makes sodium react with water and very violently. Okay, so now what you will notice is that sodium is a part of which family on the periodic table? Is it a halogen? Is it a noble gas? Is it a transition metal? Does anyone remember which family sodium is a part of? Yes, do you remember?
Isn't it the alkali?
It is an alkali. Okay, so briefly what I want you to do is transition. We're going to come back to this. Transition over to the other side or the other periodic table. Okay, and at the very top where there's that space, what I want you to do is I want you to go ahead and just put off at an angle the alkali. Okay, these are alkali metals. And it's kind of important that you put the word metals. Okay? They're the alkali metals. There are alkaline metals, but that's where? Does anyone remember? It's the second column. So we might as well name those while we're right here. Alkaline earth metals. Okay. Notice I am underlining the word metals here. That's going to be a key characteristic of what we're looking at today. For the sake of discussion, we are not going to focus on anything in the center. Okay? Those particular elements are complicated to understand, for one, and you will have more exposure to the kinds of bonds that they form and the reactions they create in high school. For our general purposes, we're just getting down to the basics here. Okay, so there's the alkali metals, the alkaline earth metals. Now, if we transition over to the other side of the periodic table, we want to go ahead and name only those that are in the gray boxes. Okay, so we're only going to name those particular families that are in the gray boxes. Does anyone remember what family is that first single gray box on the left-hand side here? What is that family called? Yeah. That's the carbon family, okay? That's the carbon family. So we're going to go ahead and name that family. Okay, so there's the carbon family. What about the next one over? David? Yeah, the nitrogen family. What about the next one over? Dylan? Yeah, the oxygen family. Okay, oxygen family. What about the next one over? This one's not by the name of the element at the top. It's actually got a special name. Hannah? Yeah, we're going to call those the halogens. That's the last one we're going to name for today. Okay, I do want you to put above all of these, however, in big, bold letters, these are nonmetals. Wow. I'm glad that it sounds like a doctor's office in here. These are nonmetals. And if we zip back over to the other side, ladies and gentlemen, we can put in big, bold letters at the top. These are metals. Believe it or not, this is a very important distinction. What we are going to find with ionic bonds especially is that metals can only bond with the nonmetal. Okay? Metals can only bond with nonmetals. There is some advanced reasoning behind this. But please understand that we first discovered this through observation and experimentation. Okay, so when we first started figuring out how things could bond together, when it comes to ionic bonding, which is what we're talking about here, ionic bonding, I'm going to have you put this down in your notes here in the back, so flip back over. That when it comes to ionic bonding, metals bond with nonmetals. This is a very important idea, and it's actually one of the key characteristics behind how we know we're looking at an ionically bonded substance. Let me give you a couple of examples of substances that are ionically bonded. Okay, I'm going to give you just a few examples here. Okay, and if we have enough time, I might even show you the creation of an ionic substance. Okay, so first things first, we are going to be looking at our alkaline and alkaline earth metals. So let's look at sodium for a moment. Okay, Na. Is there anything you know Na can combine with? Can it combine with magnesium? No, why? Because they're both metals. That's excellent. And so metals do not bond with metals. They have to bond with something on the other side of the periodic table. There's something we are very familiar with that sodium bonds with on the other side. What is it? Chlorine. Yeah, when it bonds with chlorine, it creates a substance called sodium chloride. Notice that we have a metal that is table salt. Very good. Some metal and a nonmetal. There is differences between table salts and other salts, sure. There's actually most of the chemicals we'll look at in this are salts. We just don't eat them, okay? Salts are actually a very large group of compounds or substances that are made from the combining of metals and nonmetals. Another salt would be potassium chloride. Okay, so we would write that here as, and it looks like I ran out of space, so let me add another page here. You can keep writing. You have more than enough space. Let me go ahead and add another space here. I'm going to make it ruled paper. Here we go. And so you could have potassium and chloride, so KCl. Okay, which one's the metal? Yep, potassium is our metal. And which one's our nonmetal? Yep, chlorine is our nonmetal.
Wait, is KC capitalized?
Okay, that's a great point. Anytime you write down an element like KCl, the first letter of the element is always capitalized. So K is going to be capitalized, C is going to be capitalized, but the L is not because it's not the first letter of the element. Okay? Yeah, we actually, this notation, having capitals and lowercase letters, is very important. All right? We'll look more about that in a minute. Okay, I'm going to give you a couple more ionically bonded substances here. I'm going to have you write them down on your paper, and I want you to identify the metal and the nonmetal that I'm using. Okay, so I'm going to just write a few more here. Yes, you should have a lot of space. NaF, MgO, MgCl2, and we'll talk about why that is the way it's written in just a moment. Li2O, KF. Okay, right now I just want you to go through and identify what is the metal and what is the nonmetal in each of these situations. So you can even do it like you can even use the first one as a model. Just put a little M underneath the metal and put a little nonmetal underneath the nonmetal. Don't worry about the numbers like the 2's that I've put in there. We're going to talk about why those are the way they are today as well, probably near the end of class. So let's just go ahead and take a look here. How these substances that we're looking at today. These are ionic substances because we have a nonmetal and a metal. Oh, that is just wonderful. I love it when that happens. One of my faves, you know. Okay, how about NaF? Which one is the metal here? In NaF. Which one's the metal? Drew. The Na is the metal. How about in the MgO? Which one's the metal? Hannah. Yeah, Mg is metal. And since Mg is a metal, it must be a metal here as well. Cannot change. What about in the Li2O? Okay, Drew? It is the Li is the metal. Okay, and in the KO, or KF, Will? The K is the M, or the metal. All right, so can we notice any trends here? If we look at the F, it's the nonmetal. Let me go through and fill these in real quick. I see lots of hands. Give me 1 second. Nonmetal, down here, non-metal, and over here, non-metal. All right, David, what do you notice? The metals are always in front. Ladies and gentlemen, this is like a wow moment, okay? The metals are always in front. That is true. We always list the metals first. They actually have a really cool name called a cation. We're not going to get too deep into that idea, but they are always listed first. So metals are always combined with nonmetals, and the metals are always listed first. It's kind of nice. If you think about it on the periodic table, if you're reading it left to right like you would a book, the metals come first, then we add a nonmetal second, okay? So ionically bonded substances are always named and written metal, nonmetal. And it's like you're reading across the periodic table. All right, so this is what we're working with. Okay, potassium chloride, sodium fluoride, magnesium oxide, magnesium chloride, lithium oxide, potassium fluoride. These are the 6 substances I've put up on the board. We even name them the metal first. Listen carefully one more time. Potassium chloride, potassium was named first. Sodium fluoride, sodium was named first. Magnesium oxide, magnesium was named first, right here. Magnesium chloride, again, named the magnesium first. Lithium oxide, named the lithium first. Potassium fluoride, named the potassium first. So even when they're named, we can write the metal first. Okay? Hannah. The ones with the 2's are important in the sense that if the 2 was not there, no. They don't typically form substances. Here's the next thing I want to get into today. We have to finish writing in our periodic table. So let's switch back to our periodic table and let's name a few things here. Okay, I'm going to zoom way in here. We are going to name these boxes by putting, you can either put the element symbol or the element name if you can write small enough. So what I'm going to do is I'm going to go ahead and put the symbol in the upper right-hand corner. So this first one is going to be hydrogen. Okay? And below hydrogen comes which element? Yeah, not Li, Li. We ain't lying today, ladies and gentlemen. We are writing Li. No lies here. Okay? Then we've got Na. And then K. I can. It's lithium, sodium, potassium. Below potassium is rubidium, Rb. RMB. Rubidium. No, that's not what RMB means. But, okay, cesium, CS. And then francium down here at the bottom, Fr. You know, I honestly don't know. Oh, no. All right, next to francium is rah, cheering on the team, Ra. And above Ra is Ba, barium. Yes, sir, 3 bags full. Sr is next to rubidium. By the way, both rubidium and strontium, 37 and 38, when burned, burn bright red. They're really neat. So if you've ever seen red fireworks, they are oftentimes or most likely have strontium or rubidium in them. Calcium is above strontium. You know what? We're going to do that in class, actually. Above calcium is magnesium, which will be right next to sodium, Na. And then Be here for beryllium. Let me zoom out a little bit so you can see them.
Is there any significance of why they're each of those are next to each other? Is it just because?
There is some significance. All right, listen. Hey, in 5, 4, 3, 2, 1. Can you tell me what number is in all of the boxes in the first column? Yeah. 1. Does anyone remember which electrons or the name we give to those electrons? They're very special types of electrons. Yes. Yes. Valence electrons. Please highlight, circle, star, or underline the title here. Valence electrons. This table tells you which outermost electrons or the number of outermost electrons for each of these substances. I want you to highlight, underline, circle, or star the title valence electrons. Okay. Now, there's no coincidence that this entire first column, they all have a 1, and they're all alkali metals. It's the valence electrons that determine the family an element is in. Okay? So, typically speaking, if you had 1 valence electron, you'd be an alkali metal. They all have the same chemical properties. All of these elements that have 1 valence electron are explosive with water. It's a unique property they share. So scientists, they figured this out. They said, hey, we know that lithium, sodium, potassium, rubidium, cesium, and francium, they all explode on contact with water. Hydrogen is different, but remember, hydrogen is not part of the alkali metals. Okay? And hydrogen is its own family, all by itself. So if you even want to, you can even just put a little box, a special box around hydrogen, just to show that it is not part of the norm. Okay? But these elements all have 1 valence electron. That's what makes them a family. These elements here all have 2. That's what makes them a family. We do not look at the middle block. They're really weird. Okay? So we're not going to even look at those. Now look over here at the other side of the periodic table. All of these elements here where you have aluminum, boron, okay, they all have 3, hence the reason they're all a family. And 4 in the carbon family, and 5 in the nitrogen family, and 6 in the oxygen family, and 7 in the halogens. Then there's the noble gases, and they have 8. And this leads me to the big idea for the day, or one of the main ideas, is that when a compound or a substance has 8 total valence electrons, it's stable. So let's switch back over to our notes, and I'm going to have you write that. The goal is to reach, not goat. Goal is to obtain 8 valence electrons. This little symbol right here means valence electrons. V, capital V-E dash. Okay? 8 valence electrons. That is the goal here. So, that is a capital V. It's a notation I'll use over the course of several weeks here. So, Casey, could you tell me how many valence electrons K has, potassium? So it has 1. Very good. So anywhere there's a K, I'm going to go ahead and put a 1 underneath it. Okay, so there's a K there, and there's a K there.
What would happen if an electron collided with another one?
An electron collided with another one? They just repel each other. Okay? Now, how about sodium, Na? How many valence electrons does sodium have? Sodium is Na. It's in the first column on the periodic table. So it has 1 valence electron. Okay? How about magnesium? It has 2. It's true. Lithium? Lithium has how many?
1.
Lithium has 1. Okay. Now,
Are we counting the non-metals too?
Hang on. Shh. Hang on. How about chlorine?
It has 7.
It has 7. So if I add these two, what do I get? I get 8. Okay? I get 8. Okay. So then fluorine has 7. If I add those two, what do I get? 8. Get 8. We're going to skip over MgCl2 for the time being. What does O have?
6.
It has 6. If you look on the other side of the periodic table, you'll see that it has 6. So together they have 8. Notice they all are equaling 8. Look here. O would be right here, oxygen. Okay, oxygen is right here. It has 6. This would be sulfur, nitrogen, phosphorus, carbon, a lot of it. I would definitely label them. That's good.
No one cares about business, Drew.
Okay. So oxygen has 6. And when you combine it with Mg, which has 2, it has a total of 8 outermost electrons. That is what we call, and there's a special name for that. There's a lot of special names for things. Ladies and gentlemen, this is what we call the octet rule. That means the octet rule is an idea that in order to form a substance, ionically bonded things or substances have to have 8 outermost electrons total. Okay, they have to have 8 or a multiple of 8. We'll get to that in a minute. Okay, so let's go back over here to Li2. Ladies and gentlemen, I have 2 Li's. So I don't have just one outermost electron. I have how many? 2. Because I have 2 of those Li's, I get to multiply that by 2. Oxygen has 6. What's 1 times 2? Plus 6? It's kind of. All right, fluorine. Look on your periodic table. It's what I gave it to you for. Has 7. When we add the 2, we get 8. The weird one, chlorine does have 7.
That's 14.
But there's 2 of them.
So 14 plus 2 is 16.
2 plus 14 is 16.
It's a molecule.
So this one is a little different. It's a multiple of 8. I will tell you what it looks like. This one's kind of awesome. Okay? This one, ladies and gentlemen, would look like this in real life. You don't need to know this. I just thought you might be interested in knowing it. You have Mg here, and it forms a bond with a chlorine here and a chlorine here, and it's what we call a linear model. Okay, so if we're floating around in space, it would look like a little line. Okay, and it'd have big fat chlorines on the ends, and it'd have an Mg in the middle, and so it would kind of look like this.
What does it make?
Kind of looks like that, or one of the starfighters from Star Wars. Okay.
Wait, so what would
I think it would be called a Y or a Y-wing fighter from Star Wars. Not that I'm trying to be a geek or anything. It'd be magnesium chloride. It's a salt. Okay. Okay. The Yoda mobile. That's unique, sir. That's unique. Okay. So here's what I want you to do. Right now, I want you to come up with 2 different substances that you can bond with Be. Okay, what can you attach to Be to get to 8? I don't want any 2's or any numbers. Just give me two substances, or two non-metals I can put with Be to form a substance. So we're making two substances. We're going to make one with Be, and then we're going to make another one with Be. So tell me, give me two substances I could put, or two elements I could put with Be to create an ionically bonded substance. Okay? So Be has how many valence electrons is the first question. Has 2. So you need something that has how much? 6 to get to that total of 8. Okay, so oxygen is a great one. I could put oxygen with Be. Okay, and that would be beryllium oxide. That would be a proper substance. What else? Yeah. I could put sulfur, BeS. Okay, so this would be beryllium sulfide, not a pleasant smelling substance, because when you have sulfur in there, it does smell less than desirable. Okay, so both of those substances would be okay, because they equal 8 valence electrons. How many of you feel like you have an okay grasp on this idea today? Okay, that you're trying to achieve a total of how many outermost electrons? 8 outermost electrons.